Bubbles. Everyone loves bubbles, but have you ever actually thought about the maths behind them? Well, today we're going to tell you all about it until you never want to see another bubble again. Prepare to get learned.
Soap films form when a surfactant is combined with a liquid like water, which reduces the surface tension and causes the water to thin out and stretch, rather than staying together. Surfactants like soap generally have a hydrophilic and a hydrophobic end, which create a repulsion which holds the film at a thickness. People started looking into the mathematics behind soap films in the 15th century, when mathematicians were concerned with the minimization of surface area contained by a boundary. Belgian physicist Joseph Plateau developed the technique of dipping frames into soap solutions to demonstrate the minimum geometrical area between the wire.
Now that we've had a look at history, let's take a look at mathematics. To determine the shape that this minimal area will occupy, we first prove that the mean curvature has to equal 0. To do this, the surface of the film is denoted as z equals fxy. The surface area of this film is given by the integral over here, where S represents the region of the plane on which the film is defined, and the value of f is specified on the boundary of S. The Euler-Lagrange equation can then be used to determine the shape of minimal area following the boundary conditions, where L is given over here. In subbing that value, we can rewrite that equation to this form over here. This equation states that the mean curvature must equal to 0, and therefore, by the principle of area minimization, we can simplify this to this. For this equation to be equal to 0, as we have shown must be true, the numerator must be equal to 0, which results in this form over here, known as the Lagrange equation. Minimal surfaces must satisfy this differential equation.
Bubbles can take on a whole range of minimal surfaces depending on the frames they are bound to.
The general concept is that the soap film will take the local minimum energy state, which will generally refer to minimum surface area, but will have variation due to wind and gravity.
Soap films in 2 dimensions will take the lowest distance between any set of points. For instance, in the equilateral triangle, each line will meet in the center, forming 120 degrees. For 4 points forming a square, the shortest distance does not have to be the lines meeting at the center at 90 degrees, but rather can meet at 109 degrees at some other point.
By the same process that makes free bubbles spherical, the square with a string loop demo shows that the surface tension in the film will pull the string loop into a circle, regardless of the shape of the frame. For the double loop demo, 2 separated circles will form a shape called a catenoid, rather than a simple cylinder. This state occurs at what is known as thermodynamic equilibrium.
Bubble geometry has been applied in everyday situations by engineers. It has been used in a theorem to determine the geometry with the least surface area between several lines and the minimum distance between several points. This has been applied to develop roof structures such as the West German Pavilion. The mathematics behind bubble geometry has evolved into the modern-day field of area and volume minimization. That pretty much wraps up all we have time for this week on ruining your favourite childhood pastimes with mathematics. Tune in next week and see what we ruin next.
Thanks for watching, and make sure you hit that bell so you can be notified.
And join our notification squad.
Deja vu, I just been in this place.